How to build a neural network with Python and TensorFlow/Keras. Ever wondered how your favorite AI chatbot understands your questions, or how Netflix knows exactly what show you'll binge next? Welcome to the fascinating world of neural networks. Don't worry if the term sounds intimidating. By the end of this post, you'll have built your very own neural network from scratch using Python and TensorFlow/Keras. Neural networks are essentially computer systems inspired by the human brain. Just like how our neurons connect and fire to process information, artificial neural networks use layers of interconnected nodes to learn patterns from data. What you'll need before we dive in. Essential requirements for building neural networks. Python 3.7 or higher installed on your system. Basic understanding of Python programming concepts. About 30 minutes of your time and a cup of coffee. Enthusiasm for learning something awesome. This one's mandatory. Setting up your neural network kitchen. Environment setup starts by installing required packages, including TensorFlow, NumPy, Matplotlib, and scikit-learn using pip install. We then import all necessary libraries, including TensorFlow as TF, Keras for building neural networks, layers for network architecture, NumPy for numerical operations, Matplotlib for plotting visualizations, and scikit-learn utilities for data preprocessing. Finally, we check the TensorFlow version and GPU availability to ensure proper installation and hardware compatibility. Loading and preparing our data. Every great neural network starts with good data. We'll use the famous MNIST dataset, which contains 70,000 images of handwritten digits. It's like the hello world of machine learning, simple enough to understand, but powerful enough to demonstrate real AI concepts. Data loading starts by calling keras.datasets.nist load_data, which returns training and test sets with x_train containing training images, y_train containing training labels, x_test for test images, and y_test for test labels. We print the shapes to understand data dimensions. Next, we normalize pixel values by converting to float 32 and dividing by 255.0 to scale from 0255 range to 01 range. Finally, we reshape the 28 by 28 pixel images into flattened 784-dimensional vectors using reshape with -1 and 2,828 parameters for neural network input compatibility. Quote, think of data preprocessing like preparing ingredients for cooking. Just as you wash and chop vegetables before cooking, we need to clean and format our data before feeding it to the neural network. Every successful data scientist ever. Building your first neural network. Here comes the exciting part. We're going to build a neural network with multiple layers. Think of each layer as a different level of understanding. The first layer might recognize simple edges. The second layer combines edges to form shapes, and so on. Model creation begins with Keras, sequential to stack layers sequentially. The first dense layer has 128 neurons with ReLU activation and input_shape of 784 for flattened images. Second dense layer has 64 neurons with ReLU activation for feature extraction. Dropout layer with 0.2 rate prevents overfitting by randomly setting 20% of inputs to 0. Third dense layer has 32 neurons with ReLU for complex pattern recognition. Final dense layer has 10 neurons with softmax activation for digit classification. Model.summary displays the architecture. Model compilation configures training with Atom Optimizer for gradient descent, sparse_categorical_cross-entropy loss function for multi-class classification, and accuracy metric for performance monitoring. Training your neural network. Now, for the moment of truth, training time. This is where your computer becomes a student, learning from thousands of examples. The neural network will look at each image, make a guess about what digit it is, check if it was right or wrong, and adjust its internal parameters accordingly. Training begins with model.fit function using x_train and y_train data. Epoch's parameter set to 10 means the model will see the entire dataset 10 times. Batch_size of 32 processes 32 examples before updating weights. Validation_split of 0.1 reserves 10% of training data for validation monitoring. Verbose equals 1 shows progress during training. The fit function returns a history object containing training metrics. After training completes, model.evaluate test performance on unseen x_test and y_test data, returning test_loss and test_accuracy values. Final print statement displays the accuracy as both decimal and percentage format. Visualizing the learning process. Visualization starts with plt.figure creating a 12 by 4-inch plot canvas. First subplot uses plt.subplot 1, 2, 1 for accuracy visualization. We plot training accuracy from history.history accuracy in blue and validation accuracy from history.history val_accuracy in red. Title is label as epoch, a label as accuracy. Legend and grid are added. Second subplot uses plt.subplot 1, 2, 2 for loss visualization. Training loss plotted from history.history loss in blue and validation loss from history.history val_loss in red. Similar formatting with title model loss over time is label epoch, a label loss, legend and grid. Finally, plt.title optimizes spacing and plt.show displays the dual plot visualization. Testing your neural network. Key steps for evaluating your neural network. Make predictions on new, unseen data. Compare predicted results with actual labels. Visualize correct and incorrect predictions. Calculate confidence scores for each prediction. Analyze which digits are hardest to classify. Prediction analysis starts with model.predict x_test, generating probability distributions for all test samples. np.argmax with axis equals 1 converts probabilities to predicted class indices. np.where compares predicted_ classes with y_test to find correct _ indices where predictions match labels and incorrect _ indices where they differ. Print statements show count of correct and incorrect predictions. The plot_predictions function creates visualization with plt.figure size 15 by 8. For loop iterates through first 12 indices, creating 3 by 4 subplot grid. Each image is reshaped from 784 back to 28 by 28 for display using plt.imshow with gray color map. Confidence calculated as maximum probability times 100. Title shows true label, predicted label, and confidence percentage. plt.axis off removes axis. plt.subtitle adds main title. tight_layout optimizes spacing. Congratulations! You just built and trained your first neural network from scratch. Pretty amazing, right? Your model can now look at a handwritten digit and tell you what number it is with impressive accuracy. This same fundamental approach powers everything from smartphone cameras that recognize faces to recommendation systems that suggest your next favorite movie. Taking your neural network further. Now that you've mastered the basics, here are some exciting directions you can explore. The world of neural networks is vast and full of possibilities, each path leading to new discoveries and applications. You could experiment with different architectures like convolutional neural networks, CNNs, for image recognition, or recurrent neural networks, RNNs, for text processing. Try adjusting hyperparameters like learning rate, batch size, or network depth. Quote, "The best way to learn neural networks isn't just reading about them. It's getting your hands dirty with code, experimenting with different approaches, and learning from both successes and failures." The machine learning community. Remember, every expert was once a beginner. The neural network you just built might seem simple, but it's using the same fundamental principles that power the most advanced AI systems in the world today. You're now part of an exciting community of developers and researchers pushing the boundaries of what's possible with artificial intelligence. Keep experimenting, keep learning, and most importantly, have fun with it. Enjoyed this video? Hit the like button and subscribe to stay tuned for more.